Hi everyone, my name is Rajgopal, and today I'll be talking about the structure of learnability beyond P-Poly. This is joint work with Rahul Santhanam, and this work deals with questions pertaining to efficient learnability of circuit classes. To understand what I mean by this, we first look at what Boolean circuits are, and a Boolean circuit is a computational model defined by a directed acyclic graph where the internal nodes are labeled by and or not gates, and the input variables are at the bottom. So a Boolean circuit over n inputs computes a Boolean function in the natural way. So typically, a Boolean circuit consists of and or not gates as its gates, but it could also include some other functions as part of its gate set. So commonly used complexity measures include size, which is the number of gates in the circuit, and depth, which is the length of the longest path from the output of the circuit to any of the inputs. So Boolean circuits offer a non-uniform computational model in the sense that any function has different algorithms for different input lengths. Contrast this with the uniform computation model where you have one Turing machine which computes the function on all input lengths. So finally, we define a circuit class, which is a set of all functions which are computable by Boolean circuits of a certain size or a certain depth or consisting of certain types of gates. So in this talk, we'll focus on classes of functions computable by Boolean circuits of polynomial size. And regarding the gates, I'll explain them as we get to it. So next, we'll try to understand what learning a circuit class is. For this, fix any circuit class C. So intuitively, the task of learning is that the learner receives randomly drawn examples over n-length bit strings through the distribution Dn, where the distribution is unknown but fixed. And the learning algorithm also receives the labels of each of these data points with respect to some function f in C, which is also unknown. And now, given this, the algorithm is supposed to output a good prediction for f on the data points with respect to this distribution D. In other words, the learning algorithm is supposed to output a good hypothesis, which is a good approximation for f. And when I mean a good approximation, it means that the probability that the hypothesis agrees with f on any input x drawn according to the distribution D is at least 2/3. So we call this as a random example oracle, where it supplies a randomly chosen input from D and its label according to f. And to make what I said more mathematically precise, Valiant designed this back learning framework where he said that C is back learnable using random examples if there exists a learning algorithm A, such that for every function f in C and every distribution over n-length bit strings, so given a random example oracle with respect to f and D, the algorithm A outputs a good hypothesis that approximates f well under the distribution D. And since it's a randomized algorithm, we say that it outputs the hypothesis with high probability. And furthermore, the learning algorithm is said to be efficient if it learns in polynomial time. So we can also define more powerful models of learning where we consider pack learning with membership queries. In this case, along with random examples, the learning algorithm can also query the function f on particular examples and receive its label. So intuitively, this seems more powerful than just a random example oracle access, because now the learning algorithm can actually ask for the labels of some points at the boundary, which may or may not be accessible using this random examples. So we call that such a class is learnable using membership queries. And of course, any such discussion of pack learnability is incomplete without a description of the hypothesis class. And throughout this talk, we assume that the hypothesis is a polynomial size circuit. So what classes are learnable? Like we define this notion of learnability and circuit classes, what classes are learnable. And over time, it has been shown that there are some weak concept classes which have reasonably efficient algorithms, particularly when the distribution is uniform. Examples include polysize decision trees, or with respect to circuit classes, we have polysize DNFs or polysize constant depth circuit classes like AC0 parity, which have reasonably efficient algorithms. On the other hand, more powerful classes like p-poly, which is the class of functions computable by polysize circuit families, are believed to be hard to learn. And this is because, assuming widely believed cryptographic conjectures like the existence of one-way functions, learning p-poly in polynomial time is hard. Even learning constant depth circuits with threshold gates, that's TC0, in polynomial time is hard under stronger cryptographic conjectures. So we have certain cryptographic evidence that learning these powerful classes is hard, but if we talk about complexity hardness for showing hardness of learning, then we're still very far away from proving the NP-Hardness of efficiently learning p-poly. Like an interesting result along this line was by Applebaum, Barak, and Zhao, where they showed negative results for many kinds of reductions from SAT to learning p-poly. So long story short, we have many weak classes which have reasonably efficient algorithms, but when we go to more powerful classes, it is believed that they're hard to learn, but the evidence is not as strong as one would hope. In particular, we only have hardness of learning, assuming strong cryptographic conjectures, but from complexity assumptions, we still, our knowledge is very sparse. So to remedy this, we consider a fresh perspective for hardness of learning, which is a top-down approach. And we propose the following program where we investigate learnability of circuit classes, which are much more powerful than p-poly, like x-poly or p-space poly, which are nothing but functions computable by polynomial size circuits with x oracle gates or p-space oracle gates. And our main motivation is to consider commonly held beliefs about the complexity of learning powerful classes and establish them unconditionally. So some reasons for doing this is that so we want to understand what current techniques can prove unconditionally about hardness of learning and what their limitations are for extending this to proving hardness of learning p-poly. On the other hand, we also want to investigate what structural properties strong classes like X or p-space have, which enable us in proving such results. Our first result is about unconditional hardness of learning. So a commonly believed conjecture is that learning p-poly is hard unconditionally. But of course, this has been very difficult to show since this conjecture is much stronger than separating NP from P. So we ask the question, what is the smallest class, C/poly, for which we can provably rule out efficient learning algorithms? An important caveat to keep in mind is that for classes like MAX, which is Merlin Arthur and exponential time, we already have very strong average case low bounds, and thus this trivially rules out efficient learning algorithms. The average case low bounds are against polysize circuits. So the reason for this is that if MAX cannot even be approximated by any polynomial size circuits, then of course there's no learning algorithm whose hypotheses output are going to approximate every function in MAX well. So we'll rephrase the question. What is the smallest class C-poly for which we can provably rule out efficient learners such that it is still consistent with a current understanding of complexity theory that the class C does not already have strong average case lower bounds? So to this end, we prove our first result, which is that the class BP poly cannot even be weakly learned over the uniform distribution by polytime learners, even using membership queries. So the class BP poly is a class of polynomial size circuits with BP oracle gates. BP oracle gates is bounded probabilistic exponential time, and oracle fan-in is linear in the number of inputs. So in particular, we show that BP poly cannot even be weakly learned, which means that the learner is only required to output a hypothesis which approximates the target only slightly better than probability half. And even over like a specific distribution like uniform, and even if it has membership queries. Of course, like the efficient back learnability of this class is still consistent with the current understanding of complexity theory, because we do not have any unconditional strong average case lower bounds against polynomial size circuits for this class. Our second result is based on the following conjecture, which is commonly believed, that learning P-poly must be hard in a very robust sense. In other words, the details of the learning models do not really matter. The learning algorithm could have access to random examples or membership queries. It could get data points only over the uniform distribution or any arbitrary distribution. So learning P-poly should be hard in every single model. Of course, this is very difficult to prove, but when we look at X-poly, then we show that hardness of learning X-poly over most standard models of back learning is equivalent. And in particular, and moreover, we show that they are all equivalent to proving that X is not equal to BPP. We also show that similar equivalences hold for efficiently learning P-space poly, and in this case, they're all equivalent to proving P-space not equal to BPP. So looking at the result of learning X-poly efficiently further, so X-poly is a class of functions computable by polynomial size circuits with X-oracle gates. And what we show that is the hardness of learning this class in most standard models of back learning is equivalent to showing that X is not equal to BPP. Now, X is not equal to BPP was shown by, Impalia's regression show that if X is not equal to BPP, then this is equivalent to sub-exponential de-randomization of BPP, but in the average case. So what we do here is that we end up connecting the hardness of learning a class X-poly in most standard models to one of the most fundamental questions in complexity theory, which is showing non-trivial de-randomization of BPP. So going into more detail about the kind of models for which the hardness of learning is equivalent, we show that learning X-poly must be hard in the distribution independent learning case, or even if you're learning over uniform distribution, whether we are learning using random examples or learning using query access, or whether we have worst case learning framework where the algorithm is required to output a good hypothesis for every function, or in the case of average case learning, where the learning algorithm is only required to output a good hypothesis over most inputs in X-poly according to some distribution over the functions in X-poly. So we show that the hardness of learning in all these models is equivalent to proving that X is not equal to BPP, which in turn, of course, is equivalent to non-trivial de-randomization of BPP. So I'll make a quick comment about the proofs. The proofs of these results build on techniques that were used in theory of pseudo-randomness, specifically uniform de-randomization by Impalia's regression of Trevisan-Vadhan, where they show constructions of pseudo-random generators assuming uniform hardness. Yeah. And I mean, this is not really surprising because these techniques have already been used to show that efficient learning algorithms imply circuit low bounds by Clivens, Kothari, and Oliveira. And this is a very related setting, and we try to use this for our case too. In particular, we use special properties of certain complete problems in X and P space, like downward self-reducibility or random self-reducibility, to show that learning even these functions over the uniform distribution implies that X per P space collapses into BPP. So our next set of results deals with NP-Poly, which is a non-uniform equivalent of NP. One can think of this as NP, where the verifier is a polynomial size circuit. So the question is, can we prove the NP-hardness of efficiently learning NP-Poly using random examples? So recall that Applebaum, Barak, and Zhao showed some barriers to showing the NP-hardness of efficiently learning P-Poly using random examples. And here we also prove barriers to establishing the NP-hardness of efficiently learning NP-Poly using natural Turing reduction techniques. And the kind of reduction techniques we consider are black box reductions, where a black box reduction from problem A to problem B solves A given any oracle which solves B. So having found ubiquitous use in complexity theory to establish various conditional results like worst case to average case reductions or constructions of pseudo-random generators, black box reductions have been considered to be very powerful. So we define a natural class of Turing reductions, which we call as oblivious, strongly black box reductions. What I mean by this is that oracle queries to the oracle B do not depend on the input to the reduction. Here, oracle B is an oracle to the learner, and the queries to the learner do not depend on the input to the reduction. In some more detail, so suppose we have reduction from a problem called A to pack learning NP-Poly using random examples. And we have an input X to A. So what the reduction does is that it makes queries to the oracle which pack learns NP-Poly. And any query is just like description of a random example oracle for some F in NP-Poly or some distribution D. And by the guarantees of the learner, the oracle for the learner, we get a good hypothesis HI for every Fi, which has been queried this way. So the reduction obtains a bunch of hypotheses for a bunch of queries which it makes, and it may also make it may also use these hypotheses to within itself to compute the value of A of X. So this is we call this as an oblivious reduction if the queries to the oracle L do not depend on the input X but only depend on its length. On the other hand, we call it strongly black box if the learning algorithm as well as the access to the hypotheses output by the learner is as an oracle, and we don't really use a description of any of these. So such reductions may seem very restrictive because of course you'd like the queries to depend on the input, but what we show is that the result, which we saw earlier, that P space is not equal to BPP implies hardness of learning P space / poly, actually uses these reductions. So these reductions are not, they have been utilized previously to show hardness of learning. And if we try to extend this to show the NP hardness of learning NP poly or uniform distribution using random examples with such reductions, then PH collapses to the third level. So in some sense, this gives a barrier to using currently used techniques for hardness of learning to reduce from SAT to learning NP poly or random examples. So I'll just talk by giving some future directions. Can we show the hardness of learning NP poly based on the hardness of SAT using non-black box reductions? So recently, there has been some success for using non-black box reductions for worst case to average case reductions within NP. This is work by Hirahara. And the hope is that maybe we can extend these techniques or have new non-black box reductions which show the NP hardness of learning NP poly. Another very interesting question is that can we show an analog of the PH collapse for learning? In other words, can we show that if NP poly is efficiently learnable, then is PH poly efficiently learnable as well? I feel that understanding this question would shed more light into the complexity of learning efficiently in general. With this, I'll end my talk. Thank you very much for listening.